So in our last video, we were talking about atomic theories, Dalton's atomic theories. And we said that some of those theories don't really apply today. We've got better information. Theories can change. However, a law is something that has been proven over and over and over again. It stands the test of time. So it gets the esteemed title of being a law. That's what we're going to look at here. From Dalton's theories, obviously everybody's a skeptic, so they want to go out and try to prove or disprove these theories. But there are three laws that seem to be proven true over and over again. So these three laws will stand the test of time. Nobody's been able to disprove the law of definite composition. And now, as you're going through these videos, if you need to stop and pause to take notes or write down a question that you might have, like, oh, okay, where'd you get this from? Or I got a question on this. Write yourself some notes so that we can go through that in class. Or even if you just need a little extra time to write something down, honestly, you can pause these whenever you need to. The first law, the law of definite composition. I love these laws, and I love the names of them. They make sense. It says a given compound must always contain the same elements in the same ratio in order to have the properties of that compound. Oh, okay, I like this. Definite composition. The word definite means that something's not changing. It's consistent. Composition obviously refers to what something is made of. We're referring to compounds here. One of the original theories said that atoms can join to make compounds. That's okay. I agree with that. But we are saying that in order to have the properties of a particular compound, you must have the same elements in the same ratio in order to get the same properties. So, for example, any sample of water has to be hydrogen and oxygen in a 2-to-1 ratio. H2O is water. You must have the same elements. Water must be made of hydrogen and oxygen, and it has to have the same ratio of atoms. 2 hydrogen for every 1 oxygen. Nothing else will have the same properties of water. And you can say the same about any compound. Now, another way to look at this law, 2 samples of the same compound must have the same elements in the same ratio by mass in order to have the same properties. Okay, I'm fine with both of these statements. So let's say we're looking at a particular compound. Again, it could be anything. This little pie graph is referring to sodium chloride. Sodium chloride. Okay, so any sample of sodium chloride has to have sodium and chlorine, and they have to be bonded in a 1-to-1 ratio. Nothing else will have the properties of sodium chloride. So now let's say I have 2 samples, and supposedly they're both sodium chloride. They obviously have to have the same elements. They have sodium and chlorine. And when it says the same ratio by mass, same elements, same ratio by mass. Here's kind of what we're referring to. If I look at a periodic table and I just kind of look up sodium, and it's like 22.99, so I'll say maybe 23. Sodium is about 23 grams on the periodic table. And chlorine, let's see, chlorine 35.453-ish. Okay, so it's like approximately 35-ish grams. So if I add those together, sodium chloride should have a mass of about, what, 58 grams? Approximately. I mean, I kind of rounded those numbers up of a periodic table. So the same element part, yeah, that makes sense. Any samples of sodium chloride have to be sodium and chlorine. And we could either look at the ratio as a ratio of atoms, so it has to be a 1-to-1 ratio of atoms, or you could think of it as a ratio by mass, and that's what they're trying to do here by using percentages. A ratio by mass. So any sample of sodium chloride should be approximately 39% sodium by mass. So if you take 23 grams and divide by 58, it's like doing a percent, the part divided by a whole. Any sample of sodium chloride should be approximately 39% sodium by mass. Oh, that kind of makes sense. Chlorine. If I were to take 35 divided by 58, I should get approximately 61%. That would be true no matter what my sample size is. So I could have 1 gram of sodium chloride, I could have 100 grams of sodium chloride. It kind of comes from this. And again, these masses are just off the periodic table. Sodium's mass is always 23. Chlorine is always approximately 35. So if you do like a percent composition, percent by mass, any samples should have approximately the same percent composition by mass. And again, it kind of makes sense. Chlorine's mass is about 35, which is a little bit more than half. Well, yeah, it ends up being about 61% chlorine by mass. And true of absolutely any sample. The law of definite composition. Any sample of a particular compound must have the same elements in the same ratio in order to have the same properties. Law number 2. And you've probably heard of this one. The law of conservation of mass. All right. In a chemical reaction, atoms cannot be created or destroyed. Key word here, in a chemical reaction. Earlier when we were looking at Dalton's atomic theories, it just said atoms can never be created or destroyed. But then we were like, oh, but what about nuclear reactions, nuclear fission, nuclear fusion? Yeah, we can kind of like split atoms and we can fuse different nuclei together and make new atoms. But that's a nuclear reaction. So now this law has been made a little more specific so that it is always true. In a chemical reaction, atoms cannot be created or destroyed. However, here's what you can do. In a chemical change, atoms can be separated in a compound. So maybe you have a compound and you're going to break it apart. You could do that. Atoms could be joined together to form a new compound. New compound would have new properties. Or they could just be rearranged. So, all the existing atoms are there. They're just rearranged to form new products. But here's kind of the key. In a chemical reaction, all atoms must be accounted for before and after the reaction. Oh, okay. So here's your options. Maybe you have something like this. A compound. Let's just call it compound AB. We're going to separate that into atoms A plus atom B. Okay, so I had one atom of A, one atom of B on the reactant side. I still need to have one atom of A, one atom of B on the product side. Those atoms were not created or destroyed. They're all still present, they're just in a different form. We could do the opposite. We could have A plus B forming compound AB. And again, so we had individual atoms, we're joining them together to make a compound, but they're all accounted for on both sides of the reaction. Product side, reactant side, they each have one A and one B. could get really crazy. And maybe we have something like, I don't know, AB plus CD. Let's say we have two compounds. And then after this chemical reaction, we just rearrange the atoms. So now maybe we have like, oh gosh, atom C with atom B. And then maybe we have like A plus D. Oopsie, I should put those together. A and D together. There we go. So here's our third option, rearranging the atoms. They're all still present. There's an A, B, C, D on both sides. They're just in a little different arrangement. But they're all accounted for. We didn't create any new atoms. We didn't destroy any. Now it's kind of funny because sometimes in the lab people will say, well, I did this reaction and the mass after is less than my original mass. Whoa, like I just destroyed that and my final mass is less. And if we look at these reactions, I mean, if we have the same atoms on both sides, even if they're rearranged, the total mass should be the same. Conservation of mass. If you have all the atoms accounted for on both sides, the mass before and after should be the same. Okay, look at this example. This is often what happens in the lab. Let's say you have a match, and you're burning that match. And so then people will take the mass before and after, and they'll say, whoa, the mass after is so much less. I must have destroyed atoms. No, they're all still accounted for. Mass A is the original match, which is wood, and there's also air inside of this closed container. If you honestly had some way of like burning the match in a closed container, the masses before and after would be exactly the same. When you burn that match, you form some carbon, which is what we see left over, but then you also form two gases, carbon dioxide and water vapor. If you just burn this match in the air, the carbon dioxide and water vapor are going to escape. So yeah, like if you were just to take the mass of the sides before and after, it's going to look like mass B is less. But some of the products are gases, and gases do have masses. So if we could do this reaction like in a closed container, and we could trap the carbon dioxide and water vapor produced when the match burns, then the masses really should be the same before and after. And finally, number 3, the third law, the law of multiple proportions. I like this. The name kind of hints at what this means. Atoms of different elements can join in different whole number ratios. Kind of a key, I guess. Obviously, we have to have whole number ratios in a formula because you can't have like half an oxygen atom. You either have an atom or you don't. So you're saying it's okay to join elements in different ratios, which is kind of what this visual is supposed to show. We can have nitrogen and oxygen that join in a 1-to-1 ratio, and we form a product, and it's called nitrogen monoxide. Or you could have nitrogen bond with 2 oxygens, and you could form NO2, nitrogen dioxide. Both of those compounds exist. However, if you have different ratios, be aware those compounds will have different properties. So earlier we were kind of talking about like the law of definite composition, saying that if you want to have nitrogen dioxide, you have to have nitrogen and oxygen. You have to have the same elements in the same ratio in order to have the same properties, which is true. If you want to have nitrogen dioxide, we'll look at this one later in the year. It's like a brown gas. It's actually toxic. If you want to have a compound with all these brown toxic properties, it's got to be nitrogen and oxygen in a 1-to-2 ratio. This law is saying that it would be okay to have multiple ratios. Proportion kind of refers to ratios. You could join the same elements in different ratios, but then just be aware that the final properties will be different. NO is kind of a clear colorless gas, nitrogen monoxide. Nitrogen dioxide is brown and toxic. They're both compounds of nitrogen and oxygen, but if you have a different ratio, you'll have different properties. This happens all the time in nature. For example, we've got water. H2O versus his close cousin, H2O2. H2O2 is hydrogen peroxide. They're both compounds of hydrogen and oxygen. We're going to look at them in the lab. Actually, they're both clear colorless liquids, but they do have some different chemical properties. Sometimes, like if you get your wisdom teeth out or something like that, they'll have you gargle hydrogen peroxide. If you ever tasted peroxide, hydrogen peroxide, it's not refreshing like water. I wouldn't have a good workout and then go to the medicine cabinet and down a bunch of hydrogen peroxide. It's not refreshing. It's strange. It's got a really weird feel in your mouth. It's not as stable as water, and it actually has a tendency to decompose and form oxygen gas, which is one of the reasons why they sometimes have you gargle peroxide. The oxygen gas is kind of a disinfectant. And so if you have like any, wisdom teeth out, cavity filler, or something crazy, sometimes they'll have you gargle that hydrogen peroxide. Other examples. We can have, here's a good one, carbon dioxide, actually very similar, versus carbon monoxide. Carbon dioxide, we exhale it all the time. Carbon monoxide is toxic. Same elements, just different ratios. There are different forms of iron oxide. Fe2O3 is rust. So it's got like that orangey brown, rusty color to it. Then there's this guy, FeO. That one's kind of a black powder. They look very different, and they have very different chemical properties in the lab. So you have to be kind of careful if you tell somebody, hey, go get the iron oxide. Whoa, wait a second, we have 2 bottles of iron oxide. So you have to be kind of particular if you're looking at compounds that could have multiple ratios. They're going to have different properties. So these 3 laws have been proven true over and over and over again. If you think you've disproven one of these, let me know, and then you might find yourself in a science book someday.